introduction for our topic, that is Green Theorem. Historical background. Green Theorem is a basic theorem in vector calculus that shows a relationship between a vector field circulation around a closed curve and the total rotational effect inside the region bounded by that curve. This theorem offers a strong mathematical method for converting a line integral into a corresponding double integral, which usually make difficult multivariable calculus solution easier. As a result, Green Theorem has become an important tool in mathematics, engineering, and physics. Next, Green Theorem was first introduced by the English mathematician, that is George Green, in year 1828 in his article, an article on the application of mathematical analysis to the theories of electricity and magnetism. Although his work was unknown at the first, but after he improved, it became the most significant achievement in vector calculus. Next, Green Theorem now is the most important in current mathematical analysis, since it serves as the basis for a number of complex integral theorems, such as a divergence theorem and Stokes theorem. Next, Green Theorem formula. At the slide, show that the formula, and where C is positively oriented boundary curve and R is enclosed region, P and Q is the scalar function, and dA is the differential area element. At the left-handed side of equation is the line integral evaluate along the positively oriented boundary curve C, which measure the circulation of the vector field around the boundary. Furthermore, the right-handed side of equation is represent the double integral of the scalar curve over the enclosed region, that R, which measure the total rotational effect within the region. Green Theorem state that these two of both sides are mathematically equivalent, and as illustrated in figure 1 is the circulation measure along the boundary curve that is equal to the total curl accumulate over the enclosed region, providing a geometric interpretation of the theorem. Next, the last section for introduction. Green Theorem can just be applied when some conditions are satisfied. Firstly, the curve C must be a simple closed curve, meaning that it forms a complete loop without crossing itself. Other than that, the curve must also be positively oriented, which means it is travel in a counterclockwise direction so that the enclosed region remain on the left side of the path. In addition, the function phi, p, and q, together with their first order partial derivative, also must be continuous throughout the region enclosed by the curve. When these conditions are satisfied, Green Theorem can be used to convert a line integral into a double integral. And lastly, the limitation of Green Theorem. First, the theorem is not applicable when the boundary curve is open, self-intersecting, or when the vector field is not continuous over the enclosed region. Moreover, Green Theorem only applies to two-dimensional regions, while a problem involving three-dimensional surface require to use the Stokes theorem or the divergence theorem.
For question 1, we need to evaluate the equation using Green Theorem, which is C is a closed curve by two equations, which is y equal to x squared and y squared equal to x. For the first step, as we can know from the equation given, dx represent as p and dy represent as q. Then we need to differentiate the p in term of y, that we get negative x, and then differentiate q in term of x, we get negative 9. So based on the Green Theorem, we can get the equation of negative 9 plus x. Second step is to draw the graph. So for the first equation, y equal to x squared, we get graph like this. And for the second equation, y squared equal to x, we get graph like this. Next step is to find the intersection point. First thing, for the equation of the graph given, we can substitute the second equation into the first equation, and we can get the y value. Then, from the y value, we can find the intersection point, which is 0, 0 and 1, 1. For the last step, we can use a formula from Green Theorem. We get a form of 0 to 1 and y squared to square root of y as a limit of integration negative 9 plus x in terms of dx and dy. And after the first derivative, we get the equation in terms of y, and the final answer is negative 57/20.
Next, I will explain question 2. In this question, an autonomous mobile robot moves inside a warehouse where it is influenced by two-dimensional force field. Fxy equals to x squared plus xy minus 2y and 3x plus y squared. The robot travels once around the positively oriented or counterclockwise circular path x squared plus y squared equals to 25. Use Green's theorem to determine the total work done by force field on the robot. To solve this problem, we apply Green's theorem, which converts the line integral around a closed curve into a double integral over the region enclosed by the curve. First, we identify the two components of the given vector field as P and Q. Next, we calculate the partial derivative of P with respect to y and the partial derivative of Q with respect to x. After substituting these derivatives into Green's theorem, the integrand simplifies to 5 minus x. Since the region enclosed by the curve is a circle with a radius of 5, it is more convenient to convert the integral into polar coordinates. So in polar coordinates, x is replaced by r cosine theta, and the area element becomes r dr d theta. Next, we calculate the double integral in polar form. First, we integrate with respect to r from 0 to 5. After integrating, we substitute the limits and obtain 125/2 minus 125 cos theta over 3. Then we integrate this result with respect to theta from 0 to 2 pi. The cosine terms become 0 after substitution. So the final answer is 125 pi.
Now I will show how to solve Green theorem problem using Maple. Let's start with question 1, where we need to evaluate a line integral bounded by two curves, which is y equal to x squared and y squared equal to x. To set up our integration, first we need to see the region. In Maple, we clear the memory with restart and load the plotting package. Since we want to look at this from a dx dy perspective, we write our curve as function of y and plot them parametrically. Plot 1 represent x equal to y square and plot 2 represent x equal to square root of y. When we display them together, we get a clean look at our leaf-shaped region, showing that our boundaries intersect perfectly at 0, 0 and 1, 1. Now, let's solve it using Green's theorem. First, we define our vector field component. P is x cubed minus xy and Q is 6y minus 9x. Green theorem allows us to convert this line integral into a double integral by taking the partial derivative of Q with respect to x minus the partial derivative of P with respect to y. In Maple, we define this as our integrand, which automatically simplifies to negative 9 plus x. To integrate with respect to x first, our horizontal limits go from the left curve y squared to the right curve square root of y. Our outer vertical limits for y span from 0 to 1. We run the nested int command and Maple instantly gives us the exact answer, which is negative 57/20. Let's move on to question 2. In this scenario, an autonomous mobile robot moves counterclockwise along a circular path defined by x squared plus y squared equal to 25. We want to calculate the total work done on the robot by a force field. First, we plot the robot's trajectory. Because this is circle, we use implicit plot to render the equation. To accurately show the positive orientation of the path, we use the arrow command to place a blue arrow at the top of the circle pointing left. Using display with scaling equal to constraint, give us a perfect circle of radius 5 that visually track the robot counterclockwise path. Finally, let's compute the work done. We input our force field components P equal to x squared plus xy minus 2y and Q equal to 3x plus y squared. Applying Green's theorem, the difference between our partial derivative gives us an integrand of 5 minus x. Since we are working with a circular region, integrating in Cartesian coordinates will be complicated. Instead, we convert to polar coordinates. We use the substitution command subs to replace x with r cosine theta and y with r sin theta, and multiply by the extra factor of r for a polar area element, and that gives us our integrand polar. To find the final work done, we evaluate the double integral. Our radius r range from 0 to 5 and our angle theta goes from 0 to 2 pi to cover the full circle. Maple process this and return the exact value of 125 pi.